In this video, we'll go through an example design of a simple buck converter using the design methods and design equations that we learned in this previous video on buck converter design. So that is given a sample specification, we'll come up with the parameters required to choose the L, C and the MOSFETs and the diodes. Once the design is completed, we will verify this design using extensive simulation using this tool called Plex. Since this is probably the first video that you'll be seeing where we use Plex simulation, I will also go through some details of the settings and the details of the various components that we use. So let's go through the given specifications first. The input voltage is a DC voltage that is variable. It varies between minimum of 20 volts to maximum of 30 volts. The output voltage VO is required to be very well regulated and maintain constant at 12 volts DC. The maximum ripple, I should say peak to peak ripple in the output voltage is limited to be 0.5% of the nominal output voltage. So that is 0.5% of 12 volts. 1% is 120 millivolts, so 0.5 is 60 millivolts. So 60 millivolts is the maximum peak to peak voltage that we can have in the output voltage. And the load current is specified to be from a minimum of 1 ampere to a maximum load current of 5 amperes DC current. So obviously from this specifications, the input is always higher than the output voltage. Therefore what we need is really a buck converter, and the schematic of the buck converter is shown here. So in this video we are going to come up with the values of L and C required, and also look at some of the parameters needed to select the MOSFETs and the diode. The switching frequency is not usually specified by the user. This is something that the designer selects based on several considerations, like the voltage and power ratings of the converter, the availability of MOSFETs with different switching characteristics, and a few other considerations. In this example, we are going to assume the switching frequency to be 400 kilohertz, which is typical of the given voltage and power levels that we are considering. The first step in any design process is to establish the range of variation in the duty ratio. And for a buck converter with constant output voltage, we had already established this equation to determine the range of D. And VO is 12 volts, so the minimum value of D would be 12 over V max, which is 30. I think that is 0.4, and VO 12 over V minimum of 20, so that is 0.6. So in this example, D varies from 0.4 up to 0.6, and this is useful in some of the equation that we need to determine L and C values. Next, let's look at the inductor selection. The design method that we suggested was to choose the inductance such that the peak-to-peak ripple in the inductor current is limited to some specified value. Now, since in this example there are no special requirements like CCM down to certain minimum load, no such requirements, so we are really free to choose this delta I value arbitrarily, and I have chosen delta I to be 20% of the maximum inductor current, which is the maximum load current. Now we need 4 parameters to choose an inductor, so let's go through each one of them. From the previous video on buck converter design, we derived 4 equations for each of those parameters, and the inductance L itself is given by VO times 1 minus D TS over delta IL, and we should use D minimum, which is the worst case for designing the L value. So substituting the numbers, VO is 12, D minimum we saw from the previous slide was 0.4, and TS, our FS is 400 kilohertz. So therefore TS, which is 1 over Fs, is 2.5 microseconds, and that is what is substituted here. And on the denominator we have delta IL, which is 20% or 0.2 times IO max, which is 5 amperes, and that turns out to be 18 microhenry. The next parameter we need is the peak value of the inductor current, and that we saw from the previous video is equal to the maximum load current plus 1/2 of the peak to peak ripple, and so that turns out to be 5.5 amperes. The DC bias is simply the load current for a buck converter's inductor, and therefore the DC bias is 5 amperes. And finally, the RMS current, the RMS value of the inductor current is given by this expression, the significant component based on the load current and another small component based on the peak-to-peak ripple. And for the given values here, IO max is 5 and delta IL is 1, so it's 1 squared is 1. So as you would expect, the component corresponding to delta IL is almost negligible, 1 over 12 compared to 25. Therefore, the RMS value of the inductor current is roughly equal to its DC value, which is 5 amperes. So given these 4 parameters, we can either do a physical design of the inductor ourselves or choose an inductor from available off-the-shelf components. We will be covering physical design of inductor in a later video, but I should just mention here that typically for these filter applications in a DC-DC converter, we use what are known as a powdered iron core. Now, having selected the inductor rather arbitrarily, we have to now select the output capacitor C such that the peak-to-peak ripple in the output voltage is less than the specified value. Our specification was 0.5% of the nominal output voltage of 12 volts. So we have the required equations derived in this buck converter design video. So the 4 parameters needed for the capacitor, we'll go through them one by one. The voltage rating should be greater than VO max, so we want to provide sufficient safety margin. Probably we'll select 25 volts capacitor. The capacitance value needs to be well above what is given by this expression. The delta IL was 1 that we chose in the previous slide on the design of the inductor. Delta VO is specified to be 0.5%, so it's 0.005 times VO of 12. Then we have this 1 over 8 term, and Fs is 400 kilohertz. So that comes out to be 5.2 microfarad. But again, from the previous video, we know that C needs to be much larger, at least more than an order of magnitude larger than what we obtained by this equation, because we know that the ripple is dominated mostly by the ESR of the capacitor. So we have the required equation for the maximum value of ESR as well, and that is delta VO over delta IL. And so that is this 0.005 times 12 or 60 millivolts divided by 1 amperes peak to peak, so giving us the requirement of ESR no more than 60 milliohms. And finally, the RMS current rating for the capacitor is given by this expression, and again delta IL is 1 over 2 times square root 3 is 0.29 amps is the required RMS current rating for the capacitor that we choose. Notice that the RMS current requirement is significantly smaller than the maximum load current, which is 5 amperes. Here I have summarized all the 4 parameters needed to choose the output capacitor. The main point to note here is whatever capacitor that we finally select should meet each of these 4 parameters individually. In meeting the ESR requirement of 60 milliohms, we would surely need a capacitance that is significantly larger than the minimum 5 microfarad that we saw in the previous slide. So from a data sheet, I picked a 200 microfarad capacitor, which has an ESR of slightly less than 60 milliohms. Some practical aspects related to the capacitor selection. Typically, in many DC-DC converters, we still use electrolytic capacitors, aluminum electrolytic. The reason is they are very inexpensive, and they also have this high CV product value. That is, for a given size, they have the maximum capacitance at a given voltage rating. But they also have very significant drawbacks in that they have a very large ESR value, and they also have limited RMS current rating. There are a few other electrolytic, like the tantalum electrolytic and more recently polymer electrolytic, that do better in terms of ESR and RMS current rating at a slightly higher cost, both in terms of actual cost as well as higher CV values. More recently, there are several other choices also being used in DC-DC high frequency SMPS applications. Some of them are multi-layered ceramic capacitors or film capacitors. Now, both of these types have negligible ESR values and very low ESL, negligible ESL, equivalent series inductance as well. And they also typically have high RMS current values. But the drawback, of course, is they are more expensive, and more importantly, they come in only low capacitance values, not in the several hundreds of microfarad easily. There are also another type of capacitor called the organic semiconductor electrolytic, which is also being used in mostly in the power supplies for computers. Finally, we look at the MOSFET and diode selection. For the MOSFET, we need the voltage rating, which in a buck converter is same as the maximum input voltage. And in our example is 30 volts, and we certainly want to give a sufficient safety margin, so probably at least a 50 volts part or above. The peak current rating is same as the peak inductor current. Again, in our example, it is 5.5 amperes. And for MOSFET, RMS current is an important information to choose the MOSFET, and it is equal to IO max times the maximum square root of the maximum D. So in our example, it is 5 times maximum D is 0.6. It's about 4 amperes RMS current. For the diodes, again, we need the voltage rating and the peak current rating, which are exactly the same as the one that we had for the MOSFET. And for a diode, we also need the average current. And since the diode conducts the output current or the inductor current only for a duration of 1 minus D in each 1 minus D TS, the average current is simply 5 times 1 minus D, which is 3 amperes. Next, I want to spend some time going through the simulation of the design that we just completed using Plex. So here's the schematic of the Plex corresponding to the buck example that we just now designed. But I will directly go to the simulation and go through each of these components and several waveforms. Here is the actual Plex simulation window showing the schematic of the buck converter that we just designed. So let's go through the various components one by one. So here is the input voltage source. Presently it is set at V equals 30 volts. We can certainly change the value anywhere between 30 volts and 20 volts to study the operation under different input voltage conditions. This is an ammeter that I put to measure the input current, and this is the MOSFET. And if you go inside, we can see the you can set the on-state resistance RDS on. Presently I've assumed ideal component, so I've set the R on to be 0, and there are a few other parameters that we can change which we don't need right now. Here is the buck converter's diode, and go inside that. The things that we can change are the forward voltage drop. Once again, for the ideal diode it is 0. We can also set the on-state resistance of the diode, which again is set at 0 for ideal component. Then I have an ammeter to measure the inductor current, and I also have a voltmeter to measure what we normally refer to as V sub A or V rect waveform, the switching waveform that is input into the LC filter. This is the output filter inductor L, and notice we've used the 18 microhenry that we designed for, and I've chosen to give the initial condition for the inductor current to be 0. Now this will take fairly long time to reach steady state, so in practice probably we want to give the correct initial condition so that we reach steady state almost instantaneously right at the start. But in this example, since I want to also look at the startup transients, so I given the initial condition for both the inductor current as well as the capacitor voltage to be 0. Now the inductors would have certainly some finite resistance, even though it will be very small. So the resistance corresponding to an 80 microhenry inductance of about 5 amperes nominal current is about 5 milliohms, and that is shown as an external resistance in this schematic. Then here is the output capacitor, and capacitance as we designed was 200 microfarad, and the ESR, which is shown explicitly is of 60 milliohms, 0.06 ohms, and I also have an ammeter to measure the capacitive current. Finally, this is the output load resistance, and I'm simulating a condition of maximum load current of 5 amperes. So it is 12 volts divided by 5 amperes gives me 2.4 ohms. And I have a voltmeter to measure the output voltage. And I have several scopes to measure the different waveforms. And once we run the simulation, we will actually look at the different waveforms in these scopes. So that is about the power stage. Next, we will look at the PWM, or the pulse width modulation stage, which generates the gate drive required to drive the MOSFET. So our PWM process is quite simple. We compare a control signal with a sawtooth or a ramp signal to generate the PWM waveform. The control signal is a constant shown here, and this corresponds to the required duty ratio, which with an input of 30 volts and for an output of 12 is 12 over 30 or 0.4. Now in practice or in a simulation of a closed loop controlled converter, this would come from the output of a controller that we design. Or in a practical case, this would be the output of an op-amp or from a digital signal processor. So regardless, this signal is compared with the sawtooth, and let's look at how the sawtooth is generated in Plex in this example. So we can give the minimum and maximum value, so it goes from 0 to 1. The frequency is set at the switching frequency 400 kilohertz, and to generate a sawtooth we keep the duty ratio to be 1. If you want a symmetrical triangular waveform, then the D would be 0.5, and we don't want any phase delay, so it is just 0. So this is how a sawtooth of 0 to 1 variation and a frequency of 400 kilohertz is generated. Now this is a relational operator, and there are several relationships that we can give, such as equal to or not equal, less than, greater than, and so on. The one that we're using here is greater than or equal to. So essentially whenever the signal at the dot is greater or equal to the signal at the other end, the other input, then the output is 1. If not, the output is 0. So essentially this generates 1 when the control signal is higher than the ramp instantaneously, and 0 otherwise. And that's exactly what we need to drive the MOSFET. And notice how we use these tags to connect various points without running lines. That makes it much more convenient to connect various points together. The rest of the things in the schematic are all the oscilloscopes and some of these probes. So there are two ways of monitoring various signals. For example, if you want to measure this voltage, you can put a voltmeter, or if you want the inductor current, we can put the ammeter here and then connect a probe to their outputs. The other method is to use this part called probe, and we can say that. So you can drag and put any of these parts that we want, the voltages and currents and other signals. So in this example, I will put this relational operator inside this probe part. So I can look at both the inputs as well as the output simultaneously from this probe block. Okay, so let's run the simulation and look at the various waveforms. Before we run the simulation, let me also show you some of the simulation settings or the simulation parameters under the simulation tab. So the simulation start time is 0, and the stop time I've set it as 2 milliseconds. Our switching period is 2.5 microseconds. So we are running several hundreds of switching cycles in this time period. Now I would like to urge you to refer to the Plex manual and read about the different types of solvers we have and the significance of each of these parameters, the maximum step size especially, relative tolerances, and so on. Now let's run the simulation. So simulation, start simulation, and the simulation is already completed running. I could tell that because if this is still running, you would see this word running at the top, but now it has completed the simulation. So let's go ahead and look at some of the waveforms. Actually, this has already become a fairly long video, so we will stop this video at this point, and look at the waveforms in part 2 of the same topic.